Okay, welcome to 1.7 video notes, systems of equations, and a little bit of modeling, just a little bit of modeling for today. All right, so our learning targets of today are to use a system of equations to model the real world, math in IRL, in real life, and then to solve a system of equations. Wow, remember that? Remember? Do you remember? I do. All right, cool. Okay, good. So anyway, let's look at an example. Okay, you can run zero point 0.2 kilometers every minute, and a horse can run 0.5 kilometers every minute, but it takes 6 minutes to saddle the horse before it can start running. So I'm going to define a variable to represent distance and a variable to represent time. Now, which two variables you use are completely up to you. Okay, you can use d for distance, t for time. You can use x and y, whichever you prefer. I'm going to use d for distance, and then I'll throw t. We'll go uppercase, and so lowercase t looks like an addition sign. All right. And my uppercase d's can look like zeros at times, so we'll just go lowercase d. Okay, so I want to create an equation. Okay, create an equation that represents the distance. Here we go. Holy buckets. Represents the distance you traveled with respect to the time using your variables. All right, so my variables were d and t. Okay, so this is the distance that you traveled. So me, myself, I traveled. All right, well, if you may recall this old little thing, dirt, d equals r times t, or distance equals rate times time. Wow. All right, equals rate times time. There we go. You may recall that from a previous math class. All right, so we're kind of going to use that a little bit. We're going to use that. So for myself, if I can run 2 kilometers for every minute, so my distance is 0.2 kilometers per minute, which is time. Okay, that would be my equation for myself. Distance equals the rate, 0.2 kilometers, times the time. Well, I don't know what the time is yet. All right, so then the next question asks now you don't have a lot of space here, so you can always write it just up here on the side. Okay, create an equation to represent the distance the horse has traveled with respect to time using your variables, and keeping in mind the horse didn't start running until 6 minutes after you did. Okay, the horse started running 6 minutes after you did. All right, that's very important to remember. Okay, so why don't you give this one a shot? You're going to have to do a little bit of solving on this. All right, so pause it. All right, so I'm going to kind of walk you through this one because I believe it can be a little bit complicated. So I know that the horse traveled 0.5 kilometers per minute. So there's this distance equals 0.5 kilometers per minute, and plus some value, I'm just going to call it x. All right, because the horse started running 6 minutes after you did, I have to take that into account. Well, how am I going to take that into account? Well, if it started running 6 minutes after I did, it hasn't traveled any distance at all. So my distance would be 0, 0.5. So it took 6 minutes. So it waited 6 minutes to travel 0 kilometers plus x. So if I do the math here, 0.5 times 6 will give me 3. So 0 equals 3 plus x, so x equals negative 3. So that tells me my equation is d equals 0.5 t minus 3. Okay, because the horse started running after I did. So I have to take that into account. That's where that negative 3 actually comes from. Okay. The second part of the question says, assuming you and the horse are running along the same path, all right, does the horse ever catch you? If so, when? If not, why not? All right, well, I have two equations. I have d equals 0.2 t, and that last equation, d equals 0.5 t minus 3. Okay, so I have two equations with two unknowns, all right, d and t. So I have to solve this system of equations. So there are multiple methods to solving systems of equations. You have heard of substitution, elimination. You could solve by graphing as well. Any way you do this is going to work out. Okay, we're going to do graphing later, so let's save that one. Let's do substitution or elimination. I am personally going to choose substitution because I have two variables that are isolated, the same exact variable. So if d equals 0.2t and d equals 0.5 t minus 3, I can just set them equal to each other because they represent the same variable. So 0.2t equals 0.5 t minus 3. Math it up. Negative 0.3 t, subtract this 0.5 to the other side, equals negative 3. More math, divide both sides by negative 3. So t equals 10 minutes. All right, so does the horse catch me? Yes, it does after 10 minutes. If since I got an answer, I know it catches me. Okay, there is a time where I could not get an answer. Okay, if there's a no solution, that means the horse does not catch me. That means we do not cross paths. That means I'm pretty quick, people. I'm very, very fast if a horse isn't going to catch me. And really, I mean, you know, whatever. So this is yes, yes. If someone horse catches me after 10 minutes. Catches me after 10 minutes. All right. Wow. Oh, wow. Okay. So the next portion of our next portion here asks us to graph our two equations on the same coordinate plane. So think of d as your y and t as your x. All right. Think of y equals mx plus b. So why don't you graph those two? Okay. I'm going to keep mine. I'm going to keep my distance in one color. I'll use red, and the horses in blue. Okay. So go ahead and do that. Pause the video and go. All right, so I have my two equations graphed. Okay, right here, this represents, the red represents me, and the blue represents the horse. Okay, well, why is it starting at 6-0? All right, well, the horse had to saddle up. It waited 6 minutes to start. Okay, so I started after 6 minutes. The horse started after 6 minutes. I started right away. I started running right away. All right, so you'll notice that there's an intersection point. Okay, but we'll talk about that down here. Okay, so why are we only looking in quadrant 1? Well, think about it. All right, hopefully you actually answered this question. Okay, if we think about it, our two variables are distance and time. Our two variables, okay, only represent positive. Distance and time only represents positive values. Okay, I'm not going to use negative numbers to describe time. Okay, I'm not going to use negative numbers to describe distance. All right, we only care about the positive value, so that's why our graph only looks in quadrant 1. Okay, well, what does the point where the two equations intersect represent within the context of the problem? Why don't you pause it here, okay, and answer the question. Well, in the context of the problem, it's the distance and the time at which the horse catches me. Okay. Distance and time at which the horse catches me. Okay, the distance and time. All right. What else? What's next? Here we go. How far did you travel before the horse caught you, and how long did it take? How long did the horse travel before it caught you? Okay, the first one should be easier. Second part of the question is a little bit tougher, requires a little bit more thinking. I'm going to pause the video here, give you a second to answer those and think about those questions, and we'll discuss it. All right, excuse me. So, how far did you travel before the horse caught you? Well, if you look at your graph, all right, here and up, 2, that's 2 kilometers. Okay, where else could that number have come from? Well, I noticed that, well, excuse me, I noticed at this point, I'm sorry, is actually 10 comma 2. All right, well, the 10 on the bottom represents our time, the 2 on the top represents our distance. Okay, or excuse me, the 2 going up vertically represents our distance. All right, so it traveled 2 kilometers. Okay, how long did it take the horse to catch you? Well, we found that out actually right here. It took 10 minutes for the horse to catch me, but I wrote down 4 minutes. Now, why is it 4 minutes as opposed to 10 minutes? Well, think about it like this, okay? It took me 10 minutes, but the horse didn't start running right away. The horse started running after 6 minutes, so I have to subtract the 6 minutes that it took the horse to saddle up, so it only took the horse 4 minutes to catch me. So that's where that came from. All right. Um, really, this horse time is once it started running. It took it 4 minutes once the horse actually started running. Okay. A couple things to pay attention, to when modeling is pay attention to your units. Okay. The problem could be trying to trick you. It could say you can run 2 kilometers or 0.2 kilometers every minute. A horse can run 0.5 kilometers every hour. All right. Pay attention to your units. Okay. It could say kilometers. One could say kilometers per hour. One could say kilometers per minute. One could say miles per hour. One could say miles per minute. Then you would have to do a conversion factor. All right. Those are your notes for systems of equations and some modeling, just a little bit. Okay. We'll see you soon.